Give me a second here, I need the mic up. And then I have an announcement that's going to make Shubis very unhappy. Alright. Where's my chat room? Wow, Adirondacks is here too. Tippy! Mind blowing. I know, Sterling is back. God, I hope not. Oh, God, I hope not. But Sterling would love this one. So, ever since rebuilding my linear amplifier, I have been attempting to explain an anomaly that I just can't explain. And that anomaly occurs as I change band positions on the tank circuit, on the resonant tank circuit of the tuned pi network of the output of my linear amplifier. As I go up in frequency, my power seems to multiply. And I initially thought that it was, as Shubis would say, an inaccurate measurement. So I have gone to some very great lengths to ensure that I am putting my power into a resistive load and making sure that the metering on my linear amplifier is calibrated within a reasonable percentage of accuracy. I'm going to be double checking the calibration of the meter before I go any further tonight. But what I can tell you is, at its maximum that I've been able to successfully achieve, at its maximum, I have 1,540 volts at 410 milliamps. That's 633 watts of input power, of 633 watts of DC input power. DC, not AC, not some crazy waveform that is impossible to measure the RMS value of. 633 watts of DC input to the final tubes. The circuit that I built the tubes around should only have a maximum efficiency of 60%. 60% efficiency. So multiply 633 watts times 0.6 and you get 380 watts is what the maximum I should see. 400 watts tops. 400 watts tops of the output of these tubes with 633 watts input for an AM carrier. I'm seeing 900 watts output. 900 watts. I have triple checked that measurement. And I couldn't explain it. I just couldn't. I thought to myself, okay, it's got to have something to do with some reflected power coming back from my antenna tuner, all kinds of crazy things. Parasitic oscillators may be affecting the meter readings. No, there are no parasitic oscillations. I would see them on the oscilloscope. I have had parasitic oscillations. I have. I know what they are, and I know how to spot them. But if what I believe is correct, every single person on the planet who has ever made a Tesla coil will be able to rewire their Tesla coil and test my theory. How many people do you think own a Tesla coil? 1,000? 10,000? 100,000? How many Tesla coils are out there? Think about that. Think about that. I could have 100,000 people validate my theory. Stirling effect. Need external RF meter. Yes, I have one. It's called an oscilloscope looking at the voltage, at the sinusoidal voltage swing across a resistive load. Now, to make sure that I'm not seeing any parasitic resonance like you seem to believe I'm having, all right, what I'm going to do is I'm going to tap my voltage directly at the input to the load. So I will take all reactance values out of the equation. Head on. Oh, nice. I hope they win. All right, so I need a T fitting. Let's see. I hope I have a T. My mouse keeps dying. I don't know why. And I do not... shit. Alright, let's do it this way. I can go from... N to BNC. Then I can go BNC to T, right? BNC to T. if I can go straight from PL SO239 to BNC, that would BNC male, that would be good. And there it is, SO239 to BNC male. So here's how the measurement process goes, all right? At a given power, all right, at a known power, at a known 100 watts, this is a known calibrated 100 watts. In fact, I can check it against this power meter. I have checked it against the Bird power meter. I know that this Kenwood radio produces exactly a 100 watt plus or minus 1% carrier. So I know what 100 watts is. I know what the voltage deflection is at 100 watts into a 50 ohm load. All right, the voltage is a sinusoidal waveform. So let's see. Let's do the math. All right, watts equals E squared over R resistance equals E squared over watts. No, let's do it this way. Resistance times watts. Resistance times watts equals E squared. E is the square root of resistance times watts. Okay, so this is E RMS. E RMS times 1.4 is the peak voltage, and times 2.8 is the peak-to-peak voltage on an AC sinusoidal waveform. So I know my resistance and I know my wattage. I have 50 ohms times 100 watts is 5,000. The square root of 5,000 is 70.71 volts. So 70.71 volts RMS into a 50 ohm load is 100 watts. Yeah, that's correct. Watts equals, and if you want to do it DC, watts equals amps times volts, right? So 70.7 volts into 50 ohms is, divided by 50, 1.414 amps times 70.7 is 100 watts. So 70.7 volts RMS, 70.71 actually, times 2.8 is going to give me 198 volts peak to peak. So 198 volts peak to peak across 50 ohms, sinusoidal waveform. I've already secured the job. I start on the 6th. I'll be making an announcement soon. But yeah. All right. So let's get a 50 ohm cable. And I'm going to be looking at the voltage deflection, the voltage swing, right at the load. All reactances taken out of circuit. Excuse me. Don't want that jumper cable. Let's see. How about this one? Nope. How about this one? Maybe. Where does this one go? There we go. This is the one I want. Okay. This is an RG58 cable. Yep. RG58. Here we go. We'll plug this into that. So 100 watts. Oh shit. I'm not. I need a 10-to-1 probe here. Yeah, I don't want to blow this up. Let's see. I can go 50 volts per division, right? Oh yeah, this one already does 50 volts per division. All right. Never mind. Oh no, it does. I'm sorry, 20 volts per division. All right, so 20, 40, 60, 80. I can most I can do is 160 volts peak to peak. Shoot. I need a 10-to-1 probe. Ten to 1. 10 to 1. All right. This is my DC probe. I don't want to use that. This is a 10 to 1. All right. And I'll check that for calibration. This is, let's see, Little does he know he wasn't building an app, he was discovering free. You know, this is how this kind of stuff happens, man. Where's my trigger? Trigger. Channel 2. I am on 0.1 volts per division. So yes, that is calibrated. This is 1 volt per division with my 10-to-1 probe. We're good. So if I go to 10 volts, that's 100 volts per division. Right? Yeah. 100 volts per division. I'm just going to set this inside the... do I want to do it that way? Crap, I don't want to... Let me see if I got some other way of terminating to that connector. Somewhere I used to have a BNC to binding post. Best I can do right now is BNC to mini clip. You'll note that I'm not playing any music because I want this video archived. Oh, and by the way, if I'm right about this, anyone who's built one of those Caponazzi Caduceus coils, same thing. They should be able to rewire it to my instructions and achieve the same results. So is the headline at the top referring to the massive output from the amp? Yes. Yes, it is. Why is this mouse crapping out all the time on me? This is pissing me off. Needs cheese. Ha ha. Oh, it's so funny. All right. Here we go. 21 megahertz. 21.2. I'm going. The amp is off. AM. I should see a deflection on my scope of. What did I say my peak to peak voltage is? 200 volts peak to peak. So 10, 100, 200. So I should see a deflection. Two lines in either direction. 50, 100, 200 volts peak to peak. Yes, yes. And survey says I'm only seeing about 15 watts on the meter. So let's see if this is affecting it. Yes. There's a problem with this cable. Figures. Alright, we're going to omit the cable. I'm going to stick this probe directly into the BNC connector. Like that. Okay, so there's 100 watts. The probe is only rated to 20 megahertz. Let's try one of these probes. The scope itself is only rated to 20 megahertz as well. Yeah, that's it. So I'm 3 dB down at 20 megahertz. That's why. Duh. All right. Well, doesn't matter. All right, I can calibrate my scale. In fact, let me go down in frequency. All right, 7.2 megahertz. Yep, there's my 200 volts peak to peak. So at 21 megahertz, I've exceeded the bandwidth capability of the oscilloscope to some degree. All right, it's still 100 watts. I still have the same 100 watt dissipation, but what I'm going to need to do at this point is change my scale and calibrate my deflection to 200 volts. Actually 198 volts. All right, so just under 200 volts. There's my deflection. So right now, with the way I have the scope calibrated, I've got a voltage deflection calibrated of 200 volts peak to peak, 1 division either side of the center line. All right, 200 volts peak to peak. If I go 400 volts peak to peak, that's twice the voltage. Twice the voltage produces twice the current, which is 4 times the power. Can we agree on that? Twice the voltage? Why not? It's the reason you can say watts equals E squared over R. Voltage is not equal to power. You're correct. Current times the voltage equals power. Amps times volts equals watts. Yes? In AC as well, as long as you have a known waveform, as long as you have a sinusoidal waveform, which we have. This is not a complex waveform. So if you have a 10 ohm load and you place 10 volts across your 10 ohm load, you have 1 amp. Amps times volts equals watts, 10 watts. So 10 volts across a 10 ohm load is 10 watts. 20 volts across a 10 ohm load is 2 amps. Amps times volts, 20 times 2 equals 40 watts. So if you double the voltage, the amount of power increase is the voltage squared. If you go 3 times the voltage, 30 volts, into the same 10 ohm load, you now have 3 amps times 30 volts, which is 90 watts. And again, the same holds true if you have a sinusoidal waveform, a non-complex waveform. So when I have a deflection of 200 volts peak to peak, and I go 400 volts peak to peak, I've gone from 100 watts to 400 watts. And if I have a deflection of 200 volts versus 600 volts, I've increased my voltage 3 times, and I get 3 times the current. Never mind complex waveforms, are the voltage and current in phase? Yes, because I'm in a purely resistive load. There is no reactance or minimal reactance in this load. This is a purely resistive load. This is true power, my friend. True power. So, no. The cable is a transmission line, and it is matched to the resistive load. The cable appears transparent because the characteristic impedance of the cable is also 50 ohms. There is capacitance and inductance, and along the length of the transmission line, those two balance out as long as the load at the other end matches the characteristic impedance of the transmission line. It doesn't matter. If the load is matched properly to the cable length can be any length you want. It doesn't matter. If the load is not matched, then the cable length matters, and the cable length has an effect on the result at the other end. All right, so there's my deflection. Why so sure it's matched? Well, there are some givens that I do have to make an assumption, all right? I know that the resistive load is 50 ohms. I've measured it. It's accurate. And the published specification for the cable that I'm using is 50 ohms. So I have to trust that the published specification for the cable is accurate. All right, so let's tune up on 15 meters. All right, there's my reference, 100 watts. There's my output. Huh. Oh, crap. Hello, 1, 2, 3, 4, 5, 5, 5, 5. I'm only getting 1.8 times the voltage. .8 squared, 324 watts. Remember what I said earlier about a big announcement? Forget that. So let me check my other bands, because obviously we have a frequency dependent sampling circuit that I was using to measure my voltage output at the amplifier. It was the beer talk. No, it was not. Damn it. Let's go to 20 meters. I am a little bummed though. So I'm getting, hold on a second, I'm getting 324 watts out. Yeah, you can go back to your Diet Coke. I'm getting 324 watts out for how much power in? Let's see, voltage on the plate. $1,500 volts on the plate, just under 1,500 volts. I'm going to call it 1490 times 530 milliamps times 0.53. $1,490 times 0.53 equals, well, that's more like it, 789, call it 790 watts in. 324 divided by 790. Wow, only 41% efficiency. Ugh. At least for an AM carrier. Alright. Let's try 20 meters. I'll be eating some crow tonight. At least I know the measurement that I'm taking at the load is a true and accurate measurement. I should be jotting this down. So I'm getting 324, 15 meters, 324 in, or 324 out. Let me just double check my settings here. Two, 4, 6, 8, yep. All right. Going to 20 meters. There's my 200 volts peak to peak. In the operate mode, Hello, 1, 2, 3, 4, 5, 5, 5, 5. Hello, 1, 2, 3, 4, 5, 5, 5, 5, 5, 5, 5. Hello, 1, 2, 3, 4, 5, 5, 5, 5. All right, so 2.2. 2.2 squared times 100, 484 watts. 20 meters, 484 PEP. And my carrier is 1.7. 1.7 squared, 289 watts carrier. 289 CW. 15 meters. Just to double check my PEP output. Apparently I was looking, I don't know. I don't understand how the output at the takeoff point where I was getting it was being so influenced by the change in power level. All I know is the true power delivered at the load is not what I thought it would be. Crap. Oh well. Hello, 1, 2, 3, 4, 5, 5, 5. Same PEP output. 484 watts PEP. 484 PEP. Alright, so 15 and 20 are the same. $40. This is the one I'm really interested in. What happens when I go to 40? On 40 meters, on 40 meters, .75 squared. I have a 306 watt carrier. Hello, 1, 2, 3, 4, 5, 5. And again, 484 watts PEP. Output. Well, at least I'm not losing the power that I thought I was losing when I go to 40 meters. At least I can state reasonably accurately that I'm putting out 500 watts PEP on all available bands. So 80. Tested at 3.7 megahertz. Right? That's a solid 1.8 squared. So that's 324 watts carrier in. 80 meters, 324 CW. I'm glad I did this anyway. At least I know what my true output power is. And sideband. Hello, 1, 2, 3, 4, 5, 5, 5, 5. I'm going to call that 2.25. 2.25 squared, 506 watts PEP, 506. And then 160. Okay, don't need to touch that. .160 is even a little stronger. So I've got 15, 20 volts on the plate, 400 milliamps times 0.4, 608 watts in. I should have been doing these measurements, so it's more efficient on 160 than it is on the higher bands, which makes sense. So 160 meters. .82 squared, 330 watts CW, and hello, 1, 2, 3, 4, 5, 5, 5, hello, 5, 5. I'm going to call that 2.3 squared, 529 watts PEP. .4. 608 watts carrier. Seriously. Okay, Shubis. That's all right. Yeah, I deserve that. That's fine. That's fine. I can live with myself because I pursued accurate data. I got to the truth. Okay? I can live with that. I didn't hide the data that did not corroborate my original hypothesis. I am comforted to know that it's 500 watts PEP right across the board, though. That was my goal. Well, no, it wasn't really my goal. I was hoping for a little more than that, but yeah, it is what it is. Oh well, everybody can go back to what you're doing now. Your mind should now be unblown.